Yeah, so today we're going to talk a little bit about monomials. There's a new sheet on Google Classroom which should be available in about 1 minute. I scheduled it for 9:05, so you should have access to that shortly. Um, if you kind of follow along today, then the monomials worksheet is going to be fairly straightforward. So what I want to talk about today is just what a monomial is and how it relates to the prime climb and the prime factorization that we've been working on in the past couple of weeks. So let's start off by talking about what a monomial is, and we'll have a few examples of what a monomial is. A monomial, is a product of a number and several. Oh, good morning. All right, we have full attendance today. Super. And several variables. Okay. So a monomial is a product of a number and several variables. We call the number the coefficient. And sometimes it's worth pointing out, sometimes we refer to that number as the numerical coefficient. Numerical coefficient. And when we do that, then it's because we're trying to differentiate between the numerical coefficient and the rest of the variables. So we would call the variables the literal coefficient. Okay? Literal being like letter, right? Because we use letters to describe variables, right? And then numerical being number. But in general, when we say coefficient, if we don't specify if it's a numerical coefficient or the literal coefficient, we really just mean the numerical coefficient. That's really what coefficient means. So I'll just write that. So if unspecified, coefficient refers to numerical coefficient. In fact, in my 10 years of being a full-time university student studying math, I've never heard of anyone refer to a numerical coefficient. I've never heard anyone refer to a literal coefficient. I've only ever heard anyone call the coefficient the coefficient. So we'll just stick to the word coefficient, but it is important to know that you can call different things different things. So let's take a look at what a monomial might look like. So the following are monomials. Okay, so 3x, that would be a monomial, right? It's a product of a number and a variable. Okay, so this is a monomial. This could also be another one. 21 ab squared c. Okay, it's a product of a number and several variables. This is also a monomial. Maybe 2 times pi times x times z squared. Okay. So what's important to recognize here in this this last monomial is that the coefficient, or if we want to specify the numerical coefficient, is actually 2 pi here. Even though pi kind of looks like it could be a variable, pi is not a variable. pi does not vary. Pi is a number, right? It's about 3.14, right? Approximately 3.14. So this is kind of like what would that be? 6.28. 6.28 times x times z squared, right? So that's a product of a number, that's their numerical coefficient, and the literal coefficient, which is x times z squared. Yeah, it is possible. It is possible sometimes to have an exponent that is not a whole number, right? You could have a negative exponent. You could have an exponent that's a fraction, but that makes it not a monomial anymore, okay? Because then it's not a product of variables, right? If this is negative, that means to divide. So now you're not multiplying by variables anymore. So in order for it to be a monomial, these do actually have to be positive and whole numbers as well. So we're only going to look at monomials that have exponents that are positive whole numbers. What I want to talk about today is calculating the LCM and GCF of monomials. Okay, so part of the reason why we've spent so much time on the prime climb and looking at LCMs and GCFs, which by the way is a topic that I'm hoping that you already knew how to do, right? To calculate the LCM and the GCF of numbers. But by looking at it through the eyes of a prime climb, you're looking at the prime factorization in a slightly different way, right? Instead of looking at 6 as like 2 times 3, you might be looking at as like an orange thing and a green thing, right? And then when you compare that to a number like 15, well, 15 would be like a green thing, and I don't remember what we use as 5. I think I've got it over there, and a blue thing, right? So I'm hoping that by doing that, we might have a sort of a slightly different perspective on how LCMs and GCFs could work. So let's take a look at two monomials. Let's consider the two monomials. Let's say we've got 6x squared y z cubed and 15 x cubed y squared z. Okay, so these are our two monomials. They share some variables, right? They both have variables that are x, y, and z, right? They have different amounts of x, y, and z, but in general, they share those variables. Okay. They also have coefficients that share some prime factors, right? So let's ask ourselves: can we calculate the LCM and GCF of these? Okay. So let's start off with the LCM. Let's start off with the LCM. Okay. So let's see if we can find the LCM at least of the coefficients. Okay. So let's see if we can figure out what the LCM of the coefficients are. Okay. So this is something that we have done quite a bit of, right? But let's just remind ourselves a little bit about how this works. So I'm going to split 6 up just to remind ourselves that's 2 times 3, right? And 15 is 3 times 5. Okay. So if I wanted to find the least common multiple, what am I gonna look for in those two coefficients? What do I need to find? If I wanted to find the LCM of 6 and 15, what am I trying to do? Mm-hmm. Yeah. So I'm looking for the lowest common multiple in both of these numbers. So how do the prime factors factor in here? Yeah, so these are the factors of the number, right? So if I want to find a multiple of 6, the prime factors of that multiple should have a 2 and a 3 in it, right? So the LCM is going to have a 2 and a 3, right? Now, if I go back over here to the 15, well, I know that if it's going to be a multiple of 15, it had better have a 3 and a 5 in it, right? So let's go ahead and say, okay, well, um, if if I want my LCM to be a multiple of 15, it should have a 3 and a 5. Well, here it already has a 3 in it, so let's just finish it off. And oops, that's supposed to be a 5, and put a 5 in it. Okay, so now I know that the number that I'm dealing with right here. So this LCM so far, this is going to be a multiple of 6, right? Because this is going to be 6. That's 2 times 3. It's going to be 6 times 5. But it's also going to be a multiple of 15 because here's 15, 3 times 5. So it's going to be 15 times 2, right? So I know that the number that I've chosen here is going to be a multiple of both 6 and 15, right? But I'm not done yet, right? So I've done the coefficient. Now let's think about the literal coefficient, or the variables. So now I need to find the LCM of these two things here. So how do I find the LCM of these? Any thoughts on how we could do that? Am I going to have an x in the LCM here? Yeah. Yeah, I'm definitely going to have an x. How many x's am I going to have? Why do you say 3? Yeah, just like when we were looking at the LCM of two numbers, we're going to look at okay, so here's my x's. I definitely need some x's. If I have at least 2 x's, then I'll be a multiple of this first one. But I'm not going to have enough x's to be a multiple of this one here, right? So that's no good. So we're going to need at least 3 x's. In fact, we're going to need exactly 3 x's, because if we have any more, then it's not going to be the smallest as possible, right? So we want to choose the smallest number possible that will be at least as big as all of these exponents here, okay? So I've got 2 times 3 times 5 times x cubed. I'm going to need some y's now. So I'm going to look at my y's. How many y's am I going to need? Am I going to need 1 y or 2 y's? Yeah, I'm going to need 2 y's, right? If I have just 1 y, then that'll be fine for this one, right? Because I'll be a multiple of this y. But I'm not going to have enough y's to be a multiple of y squared, right? In order to be a multiple of y squared, I need to have at least 2 y's in it, right? So that part is done. Now let's take a look at the z's, and between the two z's here, I'm gonna need three of those z's. So I'm gonna have 2 times 3 times 5 times x cubed times y squared times z cubed. Okay, that's my LCM. That's the LCM. So I'm just looking through all of the different factors. So I'm looking at the prime factorization of the coefficients first. And then I take a look at each one of the exponents of the variables, and I say, okay, well, which one is the greater exponent? Okay. So there's the LCM. Now let's think about the GCF. GCF. Let's go back to blue. GCF. Okay, so if I want to find the GCF of these two numbers, let's think about what we need to do. Okay. So we're going to start off with the prime numbers again, the prime factorization of the coefficients. And remember, we're doing the opposite thing now. For the GCF, it's the exact opposite. So what we're going to do here is we're going to say, okay, which one of these prime factors do we have in common between the 6 and the 15? What do we have in common here? We're so quiet today. Okay, do we have 2 in common? There's 2 in both of these. No. Do we have 3 in common? Yes, we have a 3 in common. 3's here and here. So the GCF of the coefficients is just 3, right? We don't have anything else in common. So we just have a single lone 3 in here. Okay, so that part is okay. Now what we're going to do is we're going to say, okay, let's look at the x's here. And how many x's do they have in common as a factor? Yeah, we got 2. We have 2 factors in common, or 2 x's as a factor in common, right? They both don't have x cubed as a factor, right? So we're looking at factors now, not multiples. So they both have 2 x's in common. So let's throw that down there. How many y's do they have in common? Just one y. Just one y. Yep. So y to the power. If you want, you could put y to the power of 1 here. I typically just write y. And then looking at the z's here. Okay, looks like they have just a single z in common. Okay, so the LCM is going to be, well, let's simplify it a little bit. There's not really much to do to simplify it, but I would like to turn this into a single number. So 2 times 3 times 5 is 30, last time I checked. So I've got 30 x cubed y squared times z cubed. And the GCF is 3 times x squared times y times z. Okay. So that's the gist of it. So that's really how what we did with the prime climb, looking at numbers, how that relates to something a little more abstract in algebra. So you can probably imagine some of the things that we might be starting to do going forward. What's something that we often use the LCM for? Like, is there a mathematical operation that we often need to use the LCM? Division sometimes, yeah. Division often will actually use the GCF. What about when we add fractions? When we add fractions, remember, we have to find the least common multiple of the denominator, right? Sometimes we call that the LCD, the least common denominator, right? Which is just the LCM of the denominators. So it's not uncommon to need to find the LCM of 2 monomials if we're adding fractions that have a monomial, as a denominator. So that's what we might start seeing going forward. So I do have a sheet that I'd like you to work on. So this is on Classroom, and yeah, I think that there's probably one more thing about LCMs that I'd like us to look at. But I'm thinking that I might try to throw that on an assignment maybe next week. So yeah, cool. So let's get started. I'm going to end the video there and try to keep it short and sweet. Okay, so we're under 20 minutes today, so that's good. Nice.